Good afternoon. Our project is from the U.S. Air Force VGH Mark II cooling system and the Carriage Yoke. My name is Kenny Candelario, and my colleagues are Mike Fisher, Jason Campbell, and Jeff Deacon.
The purpose of our project was to create a cooling system for the existing VGH Mark I. The VGH Mark I is unsafe and inefficient as it currently stands. Our requirements was to create a cooling system that goes down to negative 35 degrees Celsius ideally, and negative 25 degrees Celsius, which was required. We also had to make everything with commercially available parts in case that something broke, they were commercially available to fix. We also had to have 2-inch material stacks for the clearance. Our motivations and goals were the shock test results determine storage and transportation, and procedures for munition components. The safety and efficiency required major improvements, as I said before, and the thermal conditions impact the reliability for fuses. We are funded by the Eglin Air Force Base, which is located in Pensacola. We are to upgrade the existing VGH Mark I, and we are to focus on the thermal controllability and carriage yokes. The existing VGH Mark I was created in 1966, and it was manufactured by 1968. It is a portable tester that produces steel and steel impacts. It tests ordnance components associated with arming, fusing, and safety functions.
This is the actual display of the VGH Mark I. Right here you have a piston that shoots up. Here is the carriage yoke that holds the actual device, which is this silver thing right here. And there you have a device that when impact, basically that's what we're testing. The impact, it delivers a shock of 80 to 100 Gs, 100,000 Gs. Each test specimen is 5 to 10 pounds, and each test lasts around 40 microseconds. The recovery time is around 3 minutes, and right now the current shield is about a 1/4 inch shield.
All right, when we were doing our initial research trying to find a right material to use, which is inexpensive, we found that austenitic stainless steel works pretty well, especially the type 304. What it does is it has great resistance to cryogenic temperatures because of its FCC structure, face-centered structure, which means they're more tightly packed than a BCC structure. When it incurs any sort of stress, there's less deformation between the lattice boundaries. Also, when we finally arrived at our final design, we needed to do more research on what exactly a vortex tube is. And what it does is it takes compressed air and it basically creates a vortex inside the tube, which spins at a very rapid rate. And as it spins, it heats up. And as it goes out the hot side, it releases the hot air and then it shoots back down through the vortex and supercools to get extreme temperatures instantly. It's also not very bulky, and it's capable of very extreme cold temperatures, and there's no moving parts, which is very good for maintenance.
The purpose of an insulation, as you can see here, is to reduce the heat transfer and to prevent the condensation when we're putting the cold air. We use the flexible insulation, which is 3 inches, 3/4 inch thick, and it has an R value of 3. The R value, the bigger the R value it is the more it can resist.
Now, one of our goals was to improve the safety of the testing processes, but as well, we were able to do some research on cement methodology and lean manufacturing, and we were able to basically take internal tasks, turn them into external tasks, and that allowed us to reduce the cycle time and increase flexibility in changeover processes, which made the carriage yoke more efficient and allowed for more flexibility when testing different various material stacks.
For our safety standard, when designing this project, we went ahead and did a little bit of research, and we looked at the OSHA standards, the ASME for the compressed air. Basically, those are just for safety and how to work around it. And also, when working with flying particles, steel on steel, you also have to go ahead and look at the eye safety. So we looked at the OSHA standards and also the ANSI standards.
All right, when we were looking at initial designs, originally we were under the assumption that we had liquid nitrogen available. Also, we needed a material that was capable of heating and cooling. So what we originally thought that we would use chromium, which is what they use for heating coils. But what we found is that it's very hard to manufacture. It's very hard to bend once it's set. So what we eventually went through was the same idea of using a heating coil, but also using the stainless steel and maybe using a hollowed out tube so we could pass liquid nitrogen through it, which would effectively cool the apparatus in the center. And also what we figured we would do is take a foam enclosure and encase that jockey box coil with the styrofoam so it would keep the cold air from escaping to the atmosphere and keep it centered on the object in the middle, which is stainless steel, Styrofoam stainless steel, and we got it from commercially available beveragefactory.com, which is basically a company that sells beer products. And the jockey box is you pass liquid through it and it sits in an ice enclosure, and as the liquid goes through the tubes, it's cooled, and on the outside it's the required temperatures. As we continued to go along and we spoke more with the Air Force, we came to the understanding that it wasn't in fact liquid nitrogen, but compressed nitrogen that was available and compressed air. So what we figured we'd use the same principle as what they do for air cans. When they hold them upside down, you could freeze water to get really, really cold. So we figured to use a gas expansion chamber, which basically you'd have a pressurized nitrogen over the compressed air because there's no moisture in nitrogen, therefore there'd be no condensation on the actual fixture in case it's electronic or whatnot. And also the use of a labyrinth nozzle, which is basically, as you can see in that picture up there, it creates more resistance as it passes through the nozzle, which in turn creates more gas expansion and cooler temperatures.
Here you can see the Carriage Yoke, the first conceptual design, where this was ideal because we only needed to redesign the bottom section of the Carriage Yoke. So we went ahead, we started developing this design, and found out that the 2-inch material stack clearance would not be able to be exceeded with this design. So what we had to do on the next slide with our final design, you can see that the material stack fixture actually comes up into the top section as well. And what this does is it gives a compact design and it allows us to slide everything in and fit everything tightly. And it also gives us the 2-inch clearance needed for any material stacks, which act as a damper between the piston and the test fixture. Now, some of the things that we need to consider while cutting into the top section was to make sure that it was still structurally adequate. So since the piston comes up and impacts the test fixture mainly, there's also a damping material between the test fixture and the carriage yoke. So we determined that all the shock between the two was transferred to the test fixture and would be negligible on the carriage yoke. Therefore, the only forces that we needed to really analyze were the forces from the interior chamber assembly, which transfer axially down the 7/8 inch bolts, which are holding down onto the new carriage yoke design. So through a series of hand calculations and SolidWorks simulations, we found the max stress to be about 7 megapascals, and this gave us a factor of safety of 3.9, which was more than we needed in order to validate the design structurally. And here you can see where the cutout is for the new fixture for the redesign, where the max stress here is about 6 megapascals, and the max stress altogether comes here at the already designed area. So we knew that if it worked before, obviously the cutout was not going to affect it adversely.
Now, for the prototype, we chose to do 3D printing with the PLA material because it was readily available to us and it was cheaper. We chose to do the top, the bottom, and the material step part of the fixture, which you can see here. And it was contracted out by Professor Ziccarelli to the Make It studio upstairs in the mechanical lab. And this works because it's a functional model, even though it can't take any of the impact for testing, it works as a model for us to use.
All right, now when we arrived at our final design for the cooling system, we basically consisted of a quick couple link for a quick changeover because we wanted to have it within 3 minutes to switch between hot, cold, or whatever fixture they had. And it consists of the vortex tube for the enclosure cooling, the vortex tube for spot cooling, the flexible so you can point it to wherever, and there's also a magnet on it so you can fit to the side of the safety shield. And an air filter to remove whatever leftover moisture that might not come from the building filters if there is or isn't one. This is the spot cooler, as you guys can see here. And basically, as you can do is you can mount it up and you say you could cool any part of the fixture or even inside. And also we have our enclosure, which is basically this right here, and it goes over the fixture and the carriage yoke, and the carriage yoke it'll sit on top. And then also inside there's a nozzle just in case you want to spray onto the inside or outside or however you want. It gives more mobility. And performance of our system, when we tested inside the student shop, since it was on a building supply, we weren't given a set airflow. It was always changing. So what we did was take a bunch of different values, readings of it, and we basically found a curve or an equation for what the airflow is and what inlet pressure you would need to get the right airflow coming out. This is also what the max cold temperature we were able to see, which is negative 45 degrees Celsius at ambient temperature of 34 degrees Celsius. And also this is the best operating curve that we got for the vortex tube. And it was even at a high ambient temperature. So it just shows that if you have the right settings as far as air pressure and the airflow, that it's capable of almost 50 degree temperature drop. And this is just to show that these are a couple of readings that we got when we had unstable airflow, that the curve just went all over the place and wasn't able to barely reach past the negative 0 degrees Celsius. And if we had not enough airflow, that it's unsteady and it's very inefficient.
For our global awareness, since we are a global society now, we went ahead and incorporated English and SI units. We also, as far as part of the procedures and the risk part of the report, we went ahead and did it in a multi-language. We did it in Spanish and French. And we also went ahead and put risk and warning labels within the report just for the user would know what type of risks are involved when operating the system.
When we conducted the experiment, we made sure to follow the standards, and we went ahead and we used the safety glasses, welding gloves, and we stood clear of the testing fixture so we wouldn't get harmed.
For our whole system basically is environmental friendly. From our insulation that we use is fiber free and environmental friendly. The yoke and the carriage system is biodegradable because it's made out of the PLA fiber, and basically that's derived from cornstarch. Also, we went with compressed air, since that's more environmental friendly than what nitrogen gas or liquid nitrogen would be.
As everyone knows, cost is usually what drives any design. So we went ahead with a budget of about $2,000. We were able to come out with the cooling system total, including the hoses, fixtures, fittings, and the Carriage Yoke 3D prototype, all for under that budget.
For lifelong learning, we were able to overcome any and all obstacles. We also learned to work in teams, and we were able, we worked with outside people, like we were able to contact company and talk to clients. We studied the availability to apply skills and learn large-scale based projects, and we improved the challenger engineering skills on a global scale. This is our Gantt chart, which shows our timeline, and we were able to stay in time. We were able to stay as in everything respectively. And this is our member responsibilities. Everyone had a major role and a minor role, so everyone contributed equally and everyone participated in everything that we did.
So in conclusion, using commercially available parts, we were able to achieve a 50 degrees Celsius or greater temperature difference using the spot cooler and the vortex tube. We recommend that we keep the lab testing environment at around 77 degrees Fahrenheit or lower in order to achieve the negative 25 degrees Celsius requirement. And also we were able to improve cycle time by up to a minute and increase the safety and efficiency of the existing Carriage Yoke design by increasing efficiency with the fixture design.
As far as future work goes, we'd like to integrate the system into the existing VHT that's already there. Right now, it runs on an air compressor. We'd like to make it so that they both can run off the same air compressor rather than an individual one, which would help with the flow rates and the pressure. Also, it runs off a LabVIEW right now, so we can integrate it so that everything can be done in a click of a button, just like the system's done now. And also maybe using an additional thermocouple, therefore you can measure different temperatures, not just what's coming out of the tube or what's going onto the surface of the test fixture. And also we'd like to expand the capabilities of the vortex tube right now, because what it can do, it can heat and cool. So maybe figure out a way to use both the heating and cooling for quicker changeover, and also no need for two different parts of two different apparatuses.
This concludes our presentation. Thank you for listening.
All right, I'm going to embarrass myself. What is this? What does this do?
Okay, I can give you a quick explanation. So this is the VGH Mark I, the Air Force Research Lab. They use this where they place electronic devices into this fixture, which mounts at the top of the carriage yoke that you can see here. So what it does is it pressurizes the bottom chamber at about 100 psi, and it fires a steel piston up, which impacts the bottom of this test fixture. And then the results of this are recorded as far as will the electronics inside work after having an impact of up to 100,000 Gs.
So the question is, if I have an electronic device, will it survive an impact?
Yeah, because what they use it for right now is using fuses at the head of the missiles. So what they want to do is make sure that if a missile's punching through a wall, it's not going to set off prematurely. They want it to set off after it goes to the wall into the
Thank
roof.
you very much.
So,
I agree.
Are you supposed to be discussing that?
Yes, Pastor.
Isn't that classified?
So I have a question. Why the temperature changes?
because what they wanted is, right now when they do tests, they can't control temperature, the temperature other than what it's operating at. So they want to be able to find a way, like, if it's at a very extremely cold temperature, say it's up in a plane right now, that the electronics is still working, that the temperature changes are going to affect functionality.
With
So
an
essentially-
impact.
With impact, whether
that
it's being
temperature.
stored, anything, yeah.
Or if it even goes off when it goes, when it actually it doesn't impact.
What's the lowest temperature again?
They require -25, but the ideal lowest temperature was -35 Celsius.
And we were able to go to negative 45.
But that's with the right flow rate. Like, this is we have different variable, like, generators is what they call them, and it allows for different flow rates, anywhere from 10 cubic feet per minute to up to 40 or even higher. So the hardest thing for us was finding a air compressor that could constantly deliver that flow rate. So what we found for our dailies, we found that 25 cubic feet per minute was what we had most available most of the time, whether it's at the machine shop or elsewhere. And that's when we were able to achieve the typical drops between 25 and 35. And when we were able to, at one point, get a full 40 cubic feet per minute, we were able to achieve that -45 degree temperature.
What's the ambient temperature at 40,000 feet altitude?
That I couldn't tell you for
That's
sure.
about 70 degrees.
Minus 58.
-58. So that's lower than this operating temperature.
But at that temperature, it's also insulated by whatever is enclosed. So it's not, all that temperature is not escaping exactly into. Some of it's being absorbed by the metal around it or whatever is insulating the fixture itself.
And also, as we were touring Eglin Air Force Base, we're going through a museum, and the tour guide was giving us an example of basically a type of aircraft where also the explosives could be up inside of the aircraft, and they can actually reach higher temperatures, which is what the next group is going to show about how they reach the higher temperatures for that testing. So it could be either or cold or hot.
When you were saying nitrogen, air was more environmentally friendly, you mean because of the production aspects of the nitrogen, not because of the nitrogen itself, right?
No, yeah, the production aspect of
You know nitrogen is not.
No, I understand.
So one more, sorry. So you guys didn't do anything with the VHG at all, right? You just have it there,
It was
right?
a modification.
Yeah,
for the
we
VHG.
modified
Okay.
and improved the improvements, because since that's modified, it was in 1968. So a lot of things have changed, a lot of standards have changed. One of the biggest things for the carriage yoke, right now, the way it currently works is that they actually had to stick their hand inside the machine where the piston, and then move the stacks that protect it from the steel on steel, and basically their hands are at risk, and that's a huge OSHA violation.
So picture it like this now. In order to put the damping materials up inside of it, they have to slide it up, hold it, and then duct tape the bottom of it, which obviously causes a risk factor because the piston can fire up. So what we did was we have this fixture that slides in and out where the materials can be placed in, and it still has clearance from the piston, and nobody has to put their hand in front of the piston.
Yeah.
Gotcha. So you redesigned that part and then added the cooling, right?
Yeah.
Correct. So
Okay.
there's two phases to our side of the ground.
Sorry if I keep going.
So on top of that, this is our side of the project. You're gonna hear the other side from the other group. Also, there's two other schools also redesigning this. Our thing was just modification and improvement.
And the other group is next.
Yes.
Erin, any comments?
No?
No? Because she's been with the group, throughout 2 semesters, so she knows what's going on.